This is the original title page of Shakespeare's sonnets, as first published in 1609. It looks fairly normal for the period, except for the two horizontal lines that usually had critical information between them. The fact that they're empty is a clue that's been ignored for 400 years. We're going to look deeper. We're going to literally connect the dots, the punctuation. The TT stands for Thomas Thorpe, the publisher. Look at the italic slope of that second T. It's actually guiding us to connect this dot at 1609 to this dot at imprinted, using the sloping T as a guide. Is there any other dot that's drawing attention to itself? Well, yeah, the G dot is only about 10 times the size it's supposed to be, and so let's connect it to the D dot and to the 1609 dot, and we find we have a perfect right angle triangle. Interesting. Now, just as that second T was a guide, the dot after that second T is a guide. If we look where the 1609 dot is pointing through there and on up, it lands at the right end of the seemingly random top horizontal line, but obviously it's not random. I'm going to take that point and connect it to the G and it to the D, and again we have another second right angle triangle. Kind of makes you wonder about the second line here, and yes, same situation. The only dot left is the Aspley dot here, and if we do the same thing here, we find we've got 4 perfect right angle triangles. In fact, that last one is more than an ordinary right angle triangle. It's a perfect 3, 4, 5 triangle. We all remember Pythagorean theory from high school. 3 squared plus 4 squared equals 5 squared, yes? So, what is this really? It's actually hiding this. A perfect circle passes through all the 6 points. This is a visual representation of something called Thales' theorem, named after the Greek philosopher who scholars believe was Pythagoras' mentor. But Thales is best known as the first person to measure the height of the Great Pyramid of Giza, and he did it using the geometry of right angle triangles. Now let's complete the image by connecting the 2 remaining intersections between the circle and the horizontal lines here and here. Now obviously no one works at this level of precision just to hide some triangles. There's got to be more going on here. We must measure them. I'm going to be really quick here and spare you most of the math, but to satisfy the academics, there's a YouTube channel where true geeks can duplicate the findings and double check their accuracy, such as this divided by this equals this, which is of course pi, accurate to 3 decimal places, the world's most well-known mathematical constant, the ratio of a circle's circumference to its diameter. Archimedes calculated it almost this accurately around 287 BCE, so it's no surprise that Shakespeare would know this. But this ratio is known simply as E. Nowhere near as famous as pi, but equally important. Shows up everywhere in higher mathematics. But here's our first mystery. E was not discovered until 60 years after the sonnets were published. Sir Isaac Newton in 1669 found it as he was inventing calculus. Jacob Bernoulli in 1683 was studying a problem we all can relate to, money and compound interest. And he came up with a simple equation. It's the same formula used by banks today to calculate how much we owe on our credit card bill. Essentially, it's this. 1 is the amount that we borrowed, plus 1.718 is the maximum possible compound interest if it's calculated continuously. Total is E, or $2.718, which we owe the bank. Now, both Newton and Bernoulli concluded that the total, 2.718, was what was really important, and they ignored the 1.718 part. Consequently, it's not considered important in its own right, even today. But we'll put that aside, because what are we to make of this? 1.718, E minus 1. This dual constant has been completely overlooked by modern science, but whoever designed this knew it was just as important as E itself. Here we have a constant that's pretty much unknown to the mainstream, 1.902. It's called Brune's constant, or B2. It concerns a unique category of prime numbers called twin primes, enormously important in encryption and internet security, but here again, this important constant wasn't known until 1919, and yet there it is. What's left? This line divided by this line gives us something we're all familiar with, 1.618, the golden ratio, symbolized by the letter phi. It's been known since at least 300 BCE. We all know its connection to the Fibonacci series. Phi is the only number that if you invert it, divide it into 1, or in this case switch those lines around and divide one into the other way, it results in itself minus 1. So when we divide the lines the other way, we get that phi minus 1. Now the Fibonacci series is derived from the basic connection of that phi to phi minus 1. And if we look over on the left-hand side, we see we have E and E minus 1, a presently unknown constant, balancing perfectly the phi and phi minus 1 on the right. Fibonacci series, it's derived by adding two consecutive numbers to get the third, and repeating the process ad infinitum. The ratio of the last two numbers eventually converges to 1.61803. But there's a variant of the Fibonacci series called the Fibonacci series, which is derived by adding three consecutive numbers to get the fourth, and repeating the process ad infinitum. The ratio of these last two numbers converges to 1.8393, and its symbol is T. This phenomenon wasn't even studied, so far as we know, until about 1914, and yet here it is on the sonnets. So we have this exquisite balance. These two lines give us Fibonacci. These two give us Fibonacci. And speaking of perfect balance, if we repeat the pattern of taking these two lines and dividing by the common hypotenuse with these two opposing lines, we get square root of 3. Now the Pythagoreans believed square root of 3 was sacred because to them it represented the root of 3, the Holy Trinity. But they couldn't have known that if we invert this ratio, just as we did with the phi and phi minus 1 lines, we get another extraordinarily important constant called gamma, or the Euler-Mascheroni constant. Second only to pi and E in importance, this constant has connections to probability theory, music, and again, prime numbers. But now we're in really deep waters again, because this wasn't officially discovered by Euler until 1734. I want you to think deeply about what you're looking at here. Altogether, 9 of the world's most important math constants, 5 of which were completely unknown in 1609 when the sonnets were published. All this encrypted within just 4 dots and 2 lines. And this is only what's inscribed within the hidden circle. Remember, the 1609 dot was a guide to the right end of the top horizontal line. If we now draw a line at right angles to the common hypotenuse, or the diameter of the circle, we discover that it too is a guide from the 1609 dot here to the left end of that top horizontal line. Also, by drawing a tangent to the circle at G, parallel to the other line, it turns out to be a guide to the left end of the lower horizontal line. These lines are just hanging out at the left. Could have ended anywhere, but they didn't. Clearly, as with everything else, they're precise. Well, if we measure them, what have we got? Sure enough, another golden ratio. And taking the lower line into the equation gives us, incredibly, root 2. Looking now at the only triangle that presents itself outside the circle, it gives us root 5, almost to 5 decimal places. But it also gives us root 6. Look at the letters he's left outside this hidden circle. By G, to B, E, N, E. During the Renaissance, the letter G was often used on maps and emblems to indicate the globe, or the earth. And anciently, the Pythagoreans used the letter G to mean geometry itself, the measuring of the earth. So looking again at these TT dots connected to the G, we have in the easterly direction, E for east, and it's a 0 horizontal baseline. Now, if it's really about measuring the earth, perhaps all these lines that are radiating out from this enormous G dot, drawing attention to itself, they're all radiating out from it. Maybe they are intended to be thought of as lines of latitude. We measure this one, it's 20 degrees exactly. And this one below the horizontal baseline is 20 degrees exactly. And we have another baseline here, don't we, that we discovered the tangent to the circle. If we use that as a baseline, there's another angle here, 20 degrees. They're all perfectly 20 degrees. Makes you wonder about these two, the remaining ones that are on the circumference, the only ones that have not been measured, because they're not perfect. And so we have to measure them by trigonometry. I will spare you the math again. It's all on the YouTube channel though. But essentially we can surmise that because this is obviously oriented to the north of its baseline and this to the east, perhaps they are latitude north, longitude east. NE. Well, the numbers are here and here worked out. Is it true that they are coordinates? Let that sink in. Stunning, exquisite, all done by placement of the punctuation and 2 lines.